This is a talk called Containers at Scale. My name is Lindsay Salisbury. I'm a production engineer for Facebook. I work out of the Seattle office. I'm going to talk about a couple things today. There's some just quick agenda with this slide subtitle. I didn't remove that. Little intro overview of sort of the stuff we work on, what the goals of the system we have are, what kind of components are involved, why this stuff is important, and then sort of how SALT fits into this bigger picture we're going to talk about. So quick little intro, a little bit about me. I've been at Facebook for about 2.5 years now. Before that, I've done 4 different startups. Before that, I've worked on embedded systems and telecommunications gear. I worked at a little company called Beyond Oblivion where Tom worked when he started SALT. So some of the original ideas that went into this project were sort of derived from our work with Puppet and the time when we were working on some of that infrastructure. Since then, I've moved on, obviously, and now I'm at Facebook. I work on the team in Facebook called Tupperware. Tupperware is our container runtime system. It contains things inside the little containers. It's a cute little name. Facebook likes to use names like that. And I work specifically on the runtime aspect of this. I work at the low level. I work directly with Linux, Linux kernel, and a lot of the low level stuff. So this talk specifically is a series of talks I'm giving about our runtime system. We haven't talked too much about Tupperware publicly. We're going to start discussing this more. We have a bunch of internal tools that we've written, internal stuff that we've built that hasn't really been opened up. We've been spending the last few years making this a better system and really focusing a lot of effort and energy on being able to eventually open source a bunch of these components. So this talk is a little bit of a mix of philosophy, some ideas, some high-level things down to some low-level things. Please feel free to raise your hand if you have questions and interrupt. I'll try and save some time at the end for Q&A, but I'm going to try and show some things on a server and then sort of hop back and forth between slides. But if you have any questions, please let me know. There's going to be some conversation about low-level Linux stuff, so I'll be showing some command line things and then sort of how SALT fits into some of these bigger pictures, or the bigger picture. So really quick overview of the system that I work on. I said it's called Tupperware. I work on the part called the agent. It's, again, the runtime. It involves working with hundreds of engineers to work on this project. There are thousands of users. Pretty much most of Facebook runs on the Tupperware infrastructure, so you can imagine all the different teams interfacing with this thing and interacting with it. We run millions of containers, lots and lots and lots. We generate billions of events every day, pretty much. So this is a big system. It's pretty big. It runs, again, most of the Facebook infrastructure, the web fleet that runs the www.facebook.com runs on this. Instagram runs on top of this. A bunch of other stuff you've heard of from Facebook runs on top of this thing. The interesting thing about it, it's very complex. There's a lot of moving parts to this. One of the things we've been working on is really making this a little bit more simple and reducing some of the complexity because of the size of the thing. What happens when you have a system like this is it becomes very chaotic. And there's really 2 aspects of the chaos that are really interesting that I'm going to touch on a little bit here. One is the sort of mechanical chaos that you get from having lots and lots of machines, lots and lots of servers, lots and lots of complexity in the software, lots of variations of how to do updates and how to deploy stuff and how to roll stuff back, lots of different requirements from lots of different users. But the other chaos that's really interesting that we've been spending some time trying to figure out is the user, the chaos involved with growing and scaling the human organization. Facebook has grown pretty significantly in the last few years, the last 10 years or so in terms of engineering size. We have a lot of people working on these systems. We have literally thousands of people touching these machines or this infrastructure every day, constantly. There are constantly changes being made. There are constant diffs being posted. There are constant code changes being made. How do you manage and maintain a system like that when you have that many humans sort of touching everything all the time? So because of that, we have some goals we want to address in order to sort of deal with those issues. And one of them is determinism. When I started working on this project, In Facebook, our container runtime was pretty non-deterministic. We would often fail. We had about, I don't know what the percentage was, something like 30% of all startups failed, and we would just retry them and just like keep going. Yeah, eventually it'll work. That's not a great way to run a system like this because you end up wasting a bunch of resources. You also have to have a whole bunch of people that understand how to debug this, which gets very complicated, especially when you have new people coming in and out of the teams all the time. So determinism is a really important aspect of this. That means you put something in and you run something, you're going to get the same thing out every time. Same thing in, run the function, same thing out. It's like functional systems. We really need to have good observability. We need to be able to see what's going on in the system. We need to be able to understand what's going to happen when we poke things. We need to be able to see when things get poked. In Salt, there's these beacons and reactor things, right? This is an event-driven mechanism. We have very similar things internally in our infrastructure that will give us a signal and the ability to know when things have happened, when events have happened in certain parts of the infrastructure, and then we can respond. Now, whether we respond with humans or whether we respond with automation, those are some of the areas we have to sort of juggle. Predictability is really important because if you want to have a reliable system, you need to be able to predict it. And in fact, I would argue that reliability is more about predictability than anything else. A system can be considered reliable if you can say, in 2 weeks, this is going to crash, right? Or this is going to be rebooted in 2 weeks. At least you know ahead of time. That doesn't mean that it's just not failing in unexpected and unpredictable ways. So a big chunk of what we work on is trying to make sure we understand how the thing is going to behave when we make changes to it, when we do updates, when we add equipment, when certain events occur. So there's some parallels here to some of the stuff we've talked about and you guys have learned about here or sort of deal with Salt, with reactors and beacons and things where you can actually define up front sort of responders to things that are occurring. And we have very similar mechanisms. I'm not going to talk about those in this talk, but we do have those at Facebook. So another big thing we have to worry about is momentum. Change is a constant, is the old cliche, right? You always, the only thing that doesn't change is change. And part of this is about building a system that allows that change to occur. And I mentioned the people aspect of this. We have a lot of people joining the company. We have a lot of people churning through stuff. And in the meantime, we've been able to do things like, there was a talk given a couple months ago about our web fleet continuous push. We push, every time somebody commits a change to the web fleet, it goes out in 3 hours. Every time. It used to be a month. Then it got down to like a day, and then it got down to 12 hours. Now it's at like 3 hours, delta, right? That's a huge system running with a lot of people that's getting changed constantly. If we don't build systems that allow for those kind of behaviors, then you end up grinding things to a halt. I'm sure some of you guys have worked on infrastructure where it gets big enough to the point where it's just like you can't change much and it gets super fragile, and now you're stuck sort of like dealing with the fact that it's calcified into this really fragile system. And you can't change it anymore, and you spend a lot of time. I see a lot of people making faces and dealing with that now, probably. We have aspects of that too, but we spent a lot of work focusing on figuring out how to solve this problem so we can keep moving things forward. Okay. So I'm going to talk a little bit about the components that go into the runtime. Show you some demos and things like that. This is, well, one thing I wanted to touch on first before I go to that in the momentum part is, actually, I'm going to go back to this, the chaotic part. So chaotic systems are generally defined by, subtle inputs generate like large swings on the output, right? So it's hard to predict what the behavior is going to be on the other side. So one of the approaches that we've taken with trying to solve this problem is to very clearly understand what we're putting into the system, right? So the observability part isn't necessarily just about how the system is behaving, but it's also about how we're changing it. Right? What kind of things we're putting into this thing, how we're affecting the underlying infrastructure. Same thing with predictability. So a lot of the stuff I'm going to talk about now is about how we put the low-level pieces together that help us understand what's going to happen in the larger scale system. So we run Linux. I don't think that's a big surprise. What might be surprising to people is that we run nearly upstream Linux. We don't have a whole lot of our own patches. We employ a bunch of kernel maintainers that maintain Linux patches, but whenever we find a bug or we find an issue or we want to fix something, we fix it and push it upstream before we put it in our infra. Almost every time we try to do that. So we're not maintaining a big long patch set of Linux fixes that we aren't contributing back upstream. All the stuff I'm going to talk about here, all the components there have been fixes from us to implement stuff or to fix bugs. So Linux gives us the basic abstraction of the hardware interface, right? This is the thing that talks to a machine. It talks to the actual CPUs, talks to the memory. Gives us a bunch of useful abstractions that we can work with, processes, memory groups, systems, devices, device drivers, et cetera, et cetera, et cetera. Another big part is systemd. Systemd is a user space, is a PID1 process manager. It's had a lot of controversial discussions about this over the last few years. It's effectively the de facto standard in Linux systems now. I think there's a handful of distros that don't use systemd, but they're not, I think, Gen 2 and maybe a couple other ones. We use systemd pretty extensively and heavily because it gives us the right kind of primitives that we need in order to interact with the kernel. You can think of systemd as a user space interaction, user space window into the kernel. So some interesting things you can do with systemd, you can say system status. It'll tell you whether it's running. And when you look at this, you start getting a picture and a view of like how all of the processes are running in your machine. This is a little dev server that I run for all my prototypical stuff that I work on. And you can see that it tells us whether the system is running, and you've got a bunch of stuff in sort of a hierarchical form. Now, the cool part about systemd that allows us to that we can interface with is you can do interesting things with a thing called systemd run, which is an interface to talk to systemd over dbus to launch processes or launch services. So if I do something like this, I can do systemd bin bash. Now I've started a bash shell, but I've started that bash shell as a systemd service. So I can go over to another window here and look at the status of that particular service. And it's loaded, it's running, it's transient. It gives us some basic primitives that we can look at for observability and debuggability. I can see how it actually created this thing. The cool part is that, like, in the old days, well, still days, but in the old way of doing it, you would launch processes by using a shell, right? Because that's the way that you interface with the system calls. You go bin bash -c, some stuff to run. So, but you've got to load bash, you've got to do all this other stuff, you've got a whole bunch of other things that bash brings along with it. The concept of environment variables, the concept of processes, of threads, of C groups and stuff like that, those are Linux kernel constructs. They're not bash or shell constructs. Systemd gives us a way to use those directly without having to have the overhead of a shell. But also we get all the benefits that you get from running systemd, like good service management. So I'll talk a little bit more. I'm going to use a little bit more systemd stuff here. How do I get back to my thing? OK. So another thing that we use, and we wrote this code actually in the Linux kernel, is a thing called cgroup2. Cgroup2 is control groups version 2. You guys may have heard of control groups in Linux. This was started like 17 years ago or something like that. It's been in for a while. It's kind of hard to use, doesn't really work super well. I/O isn't really great. CPU sharing and things are pretty bad. cgroup2 is a hierarchical control group mechanism that has proper CPU sharing, proper CPU limiting, proper memory handling, and we just pushed the patches upstream for I/O latency support. So you can actually do I/O rate limiting with cgroups in Linux now, which is pretty cool. Let me show you how this is sort of interesting and why one of the reasons I like using systemd too. So go back to our systemd run thing. So systemd not only manages the process, it also manages the cgroup interaction. So I can do a thing here, and I can say property, and I want to go memory limit. And let's give this thing 256 meg. So we'll start that. Now, this is just another process. So if I look at top, I still have 64 gig of RAM. I'm not, nothing's crazy there. I can still look at proc. I'm just in a bash shell. But if I look at the service I'm running, and I forgot the name of it, so I have to go system control, wrapper run. Great. is. System status. By the way, I like doing live demos. I think that canned demos are, if you can't do it live, then you can't do it at all. That's kind of, and watch the network go down when I say that. Always never start a demo with now watch this. So you can see the memory limit here. It's using 1.5. The limit is 400 or 256 mega RAM. It's got a limit of 4,915 tasks, processes. We can change all these limits. We can do all that stuff through that systemd run interface. If you want to try and write something like this with bash, it's a lot of complexity, and it's a lot of things you have to rewrite, and it's no longer something that you can treat as an atomic thing. Right? That's a really, really interesting and important aspect of all this, is that we can make all of these things, we can set all these parameters with one operation. Right? You don't have to go through, and you don't have to deal with race conditions, you don't have to deal with locking or anything like that. All right, so let's see how this behaves if I do something like use too much memory. Oh, geez. Well, so stress is a little command line utility that will do mallocs and other sorts of things. So I started 2 threads. I told each one to use 256 megabytes, and it seems to have died. Well, it died. I'll do it again. It died because it used too much memory. And you can see the memory cgroup killer killed the process stress because it used too much memory. So why is this important? Well, this is important because we can tell all our containers now, we can properly limit all the memory and resource utilization in our containers and save the host. We never have to worry about, I won't say never, but we rarely have to worry about ooming the host. We can take care of keeping that thing alive all the time, because that's the thing that actually is the most expensive part of recovery of an operation or of a failure. If you have to reboot a machine, you have to go through the post, you have to go through the BIOS. It's also there's a lot of security implications. If you're using TPM chips and other sort of secure encryption, stuff like that, it's costly and expensive. So we'd rather keep those things up and running. So we do that by relying on something like this. There's lots of other cgroup stuff. I'm not going to give a full cgroup demo. You guys can go out and sort of read more about this. But all of the constructs that are available in cgroup v2 are available in systemd. But one other thing I want to show you really quick that is sort of interesting and makes things a little bit easier cognitively is if I go and look at the cgroup hierarchy. So this is the actual kernel interface in sys that shows you what's going on with the cgroups. If I look at init, is that where I want to be? One. System slice. So slices in cgroup are groups of processes, they're cgroups. And I look, and I've got my little run 3.0, boom. So this is the cgroup for my particular service. So I can look at all the stuff going on in here. CPU procs, CPU stat, cgroup procs, you know, what the process IDs are of everything that's going on in there. So the observability gives aspect of this is I can go now look and inspect any container or any group of processes running on a machine just by navigating this hierarchy. The cool part is it's hierarchical, right? So I can do other interesting things like start cgroups and cgroups and cgroups and cgroups, and I can have this sort of a structured hierarchy of resource limits. Okay. And Mac OS, yay, there we go. So the other thing that we use a lot of is ButterFS. So ButterFS is a file system. It's the default in SUSE, which is kind of cool. They gave me a free hat, because although you give them out anyway. ButterFS is a file system that was started about 2011, I think, or 2012 by a guy named Chris Mason, who happens to work at Facebook. And we have adopted this thing pretty full bore. Over the last 2 years, we fixed a lot of kernel bugs related to this. We've fixed a lot of stability issues. We've fixed a lot of just operational stuff. And we've done this by basically running this across most of our fleet. We've got lots and lots and lots of operational hours on this file system, and it is pretty awesome. And I'm going to show you some of the aspects of why I think it's pretty awesome. There's 2 big components of ButterFS that we care most about, and those are called subvolumes and streams. So subvolumes is basically a way to create a volume inside of the file system that you can treat as a sort of its own set of directories, or its own sort of tree. So let's create a demo volume here. So there's a demo volume. So if I look at that, and it's just a directory, it looks pretty normal, right? There's nothing really like special about it. But I can go in here, and let's go ahead and touch some files. Test 1, test 2. And then what I can do is I can create a snapshot of this thing. Called demo 2. Oops. Now I have a copy essentially, or it's a copy on write structure from demo 2 to demo. And if I modify demo 2, I'm not modifying demo, but I've gotten all the stuff that I got from demo into this other subvolume. So what this lets us do is create volumes that have common behavior, common structures, common things that everything needs. We can snapshot it and only modify the things that we care about for a particular container or for a particular host or whatever other construct we want to use. And the only cost we're incurring is the cost of the actual change. It's a copy and write file system. The other kind of interesting thing about this is if I go into demo, which is the source of demo 2, and I remove a file, it's still in the snapshot, but now the blocks that have been removed from demo are attributed to demo 2, to the other subvolume. So we get proper I/O accounting, we get proper resource accounting for what people are using with something like this. And it lets us actually see and incur costs related to I/O, related to setup and teardown and cleaning up of lots and lots of containers. We get to attribute the I/O to the appropriate place. So it's not amortized across the whole machine, it's amortized to a particular volume. Okay. Another interesting aspect of this is a thing called send streams. So ButterFS allows you to send a stream of the file system to a file that you can replay on another machine. So I'm going to send demo butter. This is a full stream of demo. Oops, I got to mark it read-only first. Oh, haha, I can't set that. There we go. Okay, so now I have a stream of that particular files of that that subvolume. It's not very big. It's only 4K. There's only one file in it. I'll show a better demo with more actual stuff in it here in a minute. But the other interesting part of this is I can send an incremental stream from one to the other. Oops, again, I have to mark it read-only. That's what you get for live demos. Cool. Now, you can actually see demo incremental is a little slightly bigger because it has more stuff in it, right? It actually has 2 files instead of just 1 because we created the other test files. And then we deleted the 1 file. Okay, so that's the basics of ButterFS. Those are the interesting parts. It has other useful things like compression. We recently added in kernel 4.14, I believe, is the upstream version, Z-standard compression. Z-standard is Facebook's compression algorithm that we open sourced a couple of years ago. It's pretty good. We can now compress ButterFS volumes internally, so we have a pretty significant savings. You can get almost a 3x. We get almost a 3x benefit on machines that have compression turned on. A lot of our servers have it turned on so that we can have a bunch of big files and they get, obviously they get compressed down automatically. Okay. So what do we use this for? Well, we put all these pieces together and we create, in our container runtime, we create immutable images. They're immutable in the sense that we don't modify the file system, we don't modify the state of the configuration at runtime. We try to do everything we can in build time while we're actually putting the thing together, and then what we ship out to every machine is just a copy of the send stream that we replay, and we get exactly what we wanted, or exactly what we put in there during the build. So this allows us to, and then when we start the container up, we just create a snapshot of it. So I'm going to show really quick how this kind of works. So I'm going to make a base volume, a base image out of this. I'm going to go ahead and install something. This is my prototype machine, so I use Arch Linux to run stuff, to test prototypes. The cool part about also focusing on Linux kernel systemd and C groups and ButterFS is that it doesn't matter so much what the distro is anymore. We're just working with Linux. So I can prototype things on my own setup that isn't necessarily like the production servers at Facebook. As long as I'm programming against those APIs, I get all the same behaviors. So I'm going to go ahead and install a pretty base image here. This is just running through Packstrap to put something together. Okay, so now I have this base volume, base image volume. It's a full file system structure, has everything I need in order to run services in it. Now I'm going to make a demo image, and this is a snapshot of the base volume. So in volume, demo image. Right, so similar stuff. If I look at the sizes and things, they're going to be about the same. 1.2 gig, geez, that's big. Should turn on compression. Right? Okay, now I'm going to do a thing, and I'm going to start this image. So one of the other nice things about systemd is it comes with a container runtime called Nspawn. Nspawn is basically Chroot on steroids is what the systemd guys call it, but really it's a container runtime that allows, it's again an interface into the Linux kernel that handles all the namespacing, all the mount setup, all the process management, and it allows you to boot systemd inside of it. So unlike other container runtimes like Docker, where they're not really a full representation of the system, and you can't really run systemd inside of Docker very easily. You have to do a bunch of hacks to make that work. With systemd Nspawn, you can run systemd inside systemd, which allows you to run systemd inside systemd. It's pretty interesting because you can start now composing systems together that are basic building blocks and putting them together in really interesting ways. And it doesn't really so much matter what they look like individually. You can treat them more like Lego bricks and start building things that way. So let's go ahead and start this demo image. So this is starting systemd inside of this container. I'm going to log in as root because I didn't set a root password. Now what's interesting is on the systemd side, I'm going to look at the status, and you can see that I'm only seeing what's running inside my container. But if I go out and I look at the host, you can see down here this machine scope, and I've got a systemd payload and everything running of my container from the host. So I have good observability, good understanding, good ability to actually see what's going on from the host level, what's going on inside my containers. If I look at the C group setup, all these things are in what's called a machine slice, and I have this machine demo image scope, which is the scope for my particular container running on the server. Okay, so I need to make some changes. I need to do some build stuff here. I need to put together an image that we can distribute, that we can send out to a bunch of servers and run. Well, I have taken the liberty of creating a contrived example of configuring an image with Salt. So this is going to set some stuff up. This is just running locally. There's a local minion. There's no master running here. In our particular model, we generally wouldn't be running something like a master, because what we're interested in doing is using all the benefits of Salt and all the state management or something like this to build the immutable image we want to run, not necessarily manage it at runtime. Because what we're interested in doing is putting everything together and shipping this thing out so that it doesn't have to change when we actually launch it. And we let systemd, which is the thing that interfaces with the kernel, do all the stuff at runtime. That gives us a really clear abstraction and really clear interface to know what's going on and to make sure that things don't change under the covers for us once an image has been deployed. Okay, so the cool part is I can run this over and over again, right? The nice part about Salt is that if it doesn't need to be changed, it won't change it. If you guys have run any other configuration management tools like Chef or Puppet, oftentimes they're pretty non-deterministic. They'll modify stuff over and over and over again, even though they don't necessarily need to. So we have this, this demo image running. Now I'm going to do something kind of interesting here, and I want to see if this works. I'm going to run an ephemeral image of this image inside the image. So this is a snapshot of the machine itself. Image right here. So I'm running a nested container. Demo machine scope with another machine inside of it. So in the cloud world, in the sort of AWS world or the VM world, you're running VMs inside machines. You're fully abstract or like fully virtualizing all the hardware. That works fine. It creates a complete isolation. But now you can actually do a lot of this kind of work without having to have virtualization. You don't incur the overhead of that. You can run images inside of images inside of images. Allows you to create these really interesting nested like Russian doll structures that you can observe, you can look at. You don't have to have any special tools here. Like all this stuff is built into the Linux kernel and built into systemd. So you can focus most of your efforts on what do you do with all the data you can collect from this thing, right? How does that actually affect your job? How does it affect your particular organization? You don't have to rebuild a lot of these core components. Okay, so now that we have, this is an interesting exercise, but whatever. All right. I'm going to start it back up again. Oh, actually, I don't want to do that. So now that we have an image of our demo image here, I want to make sure that I want to package this thing up and get it ready to ship around. So what I'm going to do is I'm going to make sure that it's read-only. Demo. And then from the base, actually I want to set the base images read-only as well. So now I have a full file system stream from ButterFS that is an incremental diff from the parent base image to the demo image, which has all the modifications that we added with the salt states. And this thing is 24 meg. So you can imagine now we ship out this base image, which we put on every machine, because it's the common base that we use for everything. And now when you have a variation and you have one image you want to ship out for one particular job or one particular task out to a machine, you only have to ship 24 meg of differences. You don't have to ship the whole thing. Right? Cool part is you can do other stuff. See if this works. Now watch this. Oops. If I compress it, now it's only 6.3 meg. So 6.3 meg to send around all these diffs, the differences of these things. And you don't have to ship the whole image around. You can just ship parts of it. It also allows you to now start a container that's essentially fully immutable in the sense that you can't modify it at runtime. You can't modify the file system at runtime. Now, how we do that is something that looks a little bit like this, where we will run what's called an ephemeral snapshot. So we don't actually mark the root file system as read-only when we run these things. We actually just create ephemeral read-write snapshots. Because as I mentioned in the chaotic system, Facebook is a big organization. There's a lot of people. A lot of times people will do things like write files to Etsy or write stuff to lib because they can and they don't know that they shouldn't, or that it's just been that way forever, and so it's really, really hard to get people to change their behavior because they have other priorities. So we'll go ahead and we'll create we'll spin up a container here. From demo.image. Now, remember I marked that read-only, so the root of that, the ephemeral snapshot I'm creating is read-only. But you can see if I look at the mount table, this is a read-write mount on slash at this subvolume. Right, and notice that systemd creates a dot file for this because it's ephemeral, it's going to go away. So I can go here and I can go Etsy, and I can, let's go ahead and modify the OS release file. All right, so that'll break. Oops, I don't have Vim. So it's there, but now I'm going to get out of this thing and I'm going to kill my container. I'm going to look at this file from the original. Doesn't matter, it's a symlink, not there. Right, so we create ephemeral snapshots of the containers that we run so that people can do whatever they want. Right, it doesn't matter how bad they coded something or like if they made mistakes or whatever else. It's not really like, it's really difficult for us to enforce that you can't write to a root file system. What we can do though is ensure that the state of the system is known when their container is torn down or when their container is restarted. Okay. So, like, why do we use these constructs? Well, we use these constructs because they create primitives for us. And primitives are things that we can just build on top of. They don't really break down into smaller structures or smaller things, right? We use C groups as a primitive. We actually don't think about things as processes very much. In individual processes, we think of them as C groups because we don't actually run anything as one process. Very few systems in the real world run one process. It's almost always that you need something along with that running next to it or aside from it, like SSH or some log streamer, log handler, some encryption thing or some compression thing. Doesn't really matter. You're always running more than one process, almost always. Other container runtime systems and other management systems have created ways around this. Docker Swarm, Docker Compose, Kubernetes does a lot of these things in order to solve the problem of putting lots of things together, right? A pod in Kubernetes is a bunch of containers that are launched as one group. Well, that's a C group, right? It's the same thing. So we're basically like using some pretty low-level primitives in the Linux kernel and not having to build things on top of that. So we get another really important aspect for managing large-scale chaotic systems is atomicity. We want to be able to do things in one operation. That's really, really important because we don't have the time. We actually don't have the control to go back and do multiple things to fix something up, right? That thing I showed about systemd run, being able to launch processes and set all those properties, you can't do that easily with bash or with shell script. If you want to do that, you got to write your own systems to make all the syscalls and make sure that they happen in the right order. Systemd's handle this for us, so we have this abstraction that creates an atomic interface that we can use to launch stuff. ButterFS subvolume streams, when we send those and we apply them on a remote machine, it will work or it won't. If it works, it worked, and we rely on the kernel to make sure that it worked. And if it doesn't work, we rely on the kernel to tell us it didn't work. But we don't have to go back and guess. We don't have to send the stream out and then like do a SHA-256 of the file system to make sure that we got all the stuff. It gives us like free error checking and free conflict detection. So if that incremental send stream can't be applied, it won't be applied. And there's no reason for us to have to go back and validate it again. So we get that atomic behavior. This gives us predictability because we know what's going to happen, right? We can build systems knowing how systemd is going to behave. We can build tests around how systemd is going to behave, and we can build tests to make sure that if it changes or if there's new things showing up, we can flag those, right? One of the hardest problems of big complex systems is signal and understanding what's actually going on internally. If I was using something like Salt, I would build some reactor things that would respond when errors occurred so that I could start understanding how the system was behaving, because I had all these atomic primitives built up. I would know that if I got this error, something happened, and I can go back and understand exactly what was going on. And because of the fact that we build things immutably, we can go back and recreate the state of the thing that caused that error and then try to understand it better. And observability, obviously these components give us the ability to look at stuff, right? If we look at this, the internals of the C group file system, right, or we look at the systemd slice, systemd stuff, there's this other interesting thing called systemd CG top, which gives us a top sort of view of C groups that are how they're behaving. You can see I'm using 4.2 gig in my user slice. This is me because of all the stuff I did in this demo. It's really, really pretty powerful. Come on, go back. There we go. Okay, so how this applies to Salt, I gave you a quick example of sort of like building an image from a base with salt states. One of the things that we're really working hard at Facebook is making sure that we have more immutability in production. We don't actually modify containers at runtime, I've said that. In the Salt world, in systems I've built in the past, I do the same thing. I use Salt to build basically treat it like a compilation step, right? You're gonna have it build the infra in the way that you want it, build all the components that you need, and then as you send those things out, you can use runtime constructs like systemd, which is the interface to the kernel, to run those things and apply those changes that you need at runtime. And you can use other basic constructs like tempfs file systems or ramfs file systems to do things that only apply transiently, right? When I did that systemd run demo, the file that it created was actually here in run in a transient scope or in a transient directory. Run is a tempfs file system, so the state of the original file system we constructed when this machine was set up hasn't changed. What's changed is that we needed a place to store transient runtime data. And systemd takes care of that, that for us so that we don't modify the file system under the covers. Okay, I'm learning the trick of how to do this, right? So the one nice part about Salt is the declarative state, right? You're actually telling Salt what you want it to do, you're not telling it how to get there. That's really important because otherwise you end up building a bunch of systems imperatively, and then you end up with something that is pretty difficult to maintain over the long term. But the nicest part, the thing I like about Salt is it actually encourages the right behavior. Because of the fact that it's using declarative, it's a declarative system and you're defining states, and it's not quite Turing complete, although you can make it Turing complete if you use Python pillar renderers and Jinja and stuff like that. It encourages the right behavior, which is to think about the desired state you want the system to be in. And then you can focus more on the observability and predictability parts so that you can understand how those pieces fit, right? Rather than having to like worry about a flood of constant changes and constant states that you don't understand. And a little quote I like to throw at the end of the talks, how you build is more important than what you build. Because the mechanisms you use at the low level, like building runtimes out of these sort of basic primitives, express themselves pretty drastically when you start getting lots and lots of users and lots of machines interacting with these things. And so think really carefully about how you put the pieces together at the bottom, because it's going to affect how they work at the end and at the top pretty drastically. And as you're growing your companies, you're growing your infrastructures, if you do it right first, you're going to save yourself a whole lot of time because it's really, really, really hard and really, really expensive to go back and fix it. There are very few companies, I think, that have the ability to go back and do that. It's a pretty rare event. Okay, thanks. Any questions? Four? Okay. So the question was ButterFS versus ext4 journaling. How do they compare performance-wise? They're definitely completely different internal structures. We don't run ext4. We run mostly XFS and ButterFS for stuff, so I don't have great direct numbers in our infrastructure of how they perform. But for basic operations and for streaming operations, they're actually pretty comparable. ButterFS oftentimes is a little bit faster mostly because of the compression and the B-tree structure that it covers. ButterFS does not do journaling. It's not a journaling file system. I mean, it has a buffer that it writes to, and then it flushes that buffer out. But it's a different journal structure, or it's a different structure than XFS. But it is I mean, it's safe. Yeah, it recovers great. Yeah. So the question was, you have all these images running on these systems, and you push them out, now you have to change base. Right, so this is one of the complex problems that you have with something like a Docker file, right, where you change the root of what all the Docker files are generated from, and you have to rebuild the whole tree. So we don't get away from that problem with ButterFS and with the layering. You still have a tree structure, you still have to rebuild the hierarchy. The difference that this has allowed us to do is we can decouple the time requirement. You can build independently of deployment. So we can have background processes that are constantly rebuilding images, whether or not they're ever deployed, so that we're ready to go if there is a need to sort of reconstruct everything. So when we rebuild our base image, we will generally rebuild the base image plus all of the descendants in the same cycle, so that we have them available to us. And that works for us because we can ship out only what we need. But there are some other things that we haven't talked about yet, but that we're working on, where you can take two different images, the image of your service with all of its dependencies, and then your base image, and you bind mount them together, and you use systemd to compose them at runtime. So Leonard Pottering gave a talk on a thing called portable services a couple months ago. This is a new thing in systemd 239, and this is a concept we're prototyping in right now, where we can basically have one base image that people don't have to build against. They build a separate image that has their service, and we stick the two things together at runtime, and we get all the immutability benefits and all the same benefits we get from these primitives, but we don't have to have that tree build. I compare it to inheritance versus composition. Okay. Yes. Well, they're isolated as much as Linux will isolate them. Anyone who tells you that containers are secure is crazy. They're not really secure. Most of them require capsysadmin, which is the basically root access. We're working to try to fix that in the kernel. It's a Linux kernel issue more than anything. But in terms of, besides that, they're isolated. They're fully isolated from the mount file system. They're pivot rooted. They have a separate PID namespace. They have a separate IPC namespace. We don't use user namespaces because that's still somewhat broken in the Linux kernel. But they're about as isolated as you can get with containers right now. But they're not VMs, right? They're still not VMs. If you need security, you need real security, you need to use a VM. Yep. Yes. I can tell you, I don't know exactly what the internal reasons for Red Hat dropping ButterFS were. I think that because Facebook employs all the maintainers is probably why. And also Red Hat has to maintain super old kernels for their RHEL stuff. And backporting the fixes is very, very difficult. And they've invested almost heavily entirely in XFS. And there's some similar XFS concepts coming out from Red Hat that are like ButterFS, but they're obviously having to work backwards from XFS structures to try to sort of put those in place. And what was the second part of your question? Yeah, ButterFS isn't going away. It's going to be here for a long time. Like I said, we are heavily invested in it. We employ the maintainers. It runs on a large swath of our fleet. We have put millions of hours into testing this thing, and it runs all the time, and it's pretty stable, and it's not going away. And it's a good file system, and SUSE uses it. And I don't think they're going away, hopefully. So, any other questions? Nope. Cool. Thanks, everybody. Appreciate it.